It's like a ballistic expert.
We saw a grave, and
Yeah.
that's what
So we are talking about phase diagrams and what of pure compounds, and the state that's the most stable is the state with the lowest what? What type of energy? Gibbs energy, or chemical potential is the terminology. And in the chemical potential, I think that was last chapter. We said that the chemical potential is the molar Gibbs energy for pure compounds. Well, two of us did, I guess. Okay, but
As soon as the test was over, we both looked at each other. We're downstairs. We're like, "Did you put true?"
all right, good deal.
Adriana, to answer your question, yes, my brain's working. Again, as much as it.
So let's take a closer. This is where we left off, was with water, right? Well, let's go back to the dry ice idea briefly here, because what I'm thinking is what's stopping anybody from pick a pressure, pick a temperature, and be right here? Can you be there? That's definitely with the dry ice region, right? It's really cold and it's in the solid region. It's definitely dry ice. But can I physically be at that point on the phase diagram in real life here, sitting this stuff right? Some dry ice from HEB, put it out here, get the pressure, and can I do that? Well, I could stick it in a container, seal it up.
That's how you get it.
What's going through my mind is, maybe it's a trick question, maybe it's not. What's going through my mind is, can you stop the equilibrium? Because now what's the equilibrium I'm talking about with this dry ice? Physically sitting here. It's going to be what state to what state, bouncing back and forth? Solid to gas. Can you stop that?
Not in reality.
I don't see how, right? So where are you going to be? Because where's equilibrium on this plot between the solid and the gas? Where's equilibrium at? It's always on the lines. So what I'm thinking is seems to me I got to be on this line here, right? If I'm at some particular pressure and temperature, and I have that equilibrium going on between those two states, I'm going to be on that line. Right? Does that make sense? Okay. So let's take a closer look at water. So there's a lot of temperatures and Kelvin and pressure and atmospheres that we can take a look at, but recognize that it's the same general configuration. Solid, really high pressure, low temp. Crank up the temperature really high, keep the pressure really low. Typically, they're always one. Crank up that temperature so it's really high. Pressure somewhat low, you're going to be in what state? The vapor, right? The gas. And then in between, intermediate temperature and pressure, liquid. So it's in general, that's pretty much how everything seems to be working. And then you see all these different ice 1, ice 2. Adriana, what the heck is going on there? Ice 1, ice 5, ice 6.
Degrees of gold.
That's all I can think of. I have no idea what
Ice 5 is probably like Minnesota.
And you crank up the pressure even more, it goes to ice 6. Something has to be changing. What could possibly be changing? Go from to call something ice and give different numbers. What is ice? Well, solid, but more specifically. And then if you crank up the pressure, it actually changes states to a different type of solid.
The bond angles or something?
The C word I think of. Now, this is where Emily's going to go nuts. CR, is
I got nothing.
crystals, right? Just changing different crystalline configurations. When you say, because I don't know, when I say crystal, I'm thinking of some orientation, right? And it's fixed, lattices and all those sorts of things, right? Now, I'm not so big on this. I know face-centered cubic, all the body-centered cubic, the typical general things, but there's going to be a lot more than that, right? So this just change, they're actually, ice, crank up the pressure is different states of the solid, different crystalline structures, okay? And crystalline may be too strong of a word even for ice, because I think of ice as more amorphous, that it's like blah, blah, right? If there's an orderly structure, there must be, otherwise you couldn't characterize ice 1, ice 2, ice 3, ice 4.
Is there a way to visually do that?
What spectroscopy? Now this, we don't have this,
No.
but
And even if we did,
to do this diffraction, it's, UTSA has an instrument on it, and I was talking to the guy who did it, and he's getting his PhDs on this. He says that it's super, super frustrating, because what you need, because the computer does all the work. The problem is getting this really nice, beautiful little crystal. The little organic guy or the project, that's what you really need. You're making all these crystals. And then, but once you get it, you put it in this machine called a X-ray diffraction or diffractometer, and I'm sure they have fancier names that sell it better. But that's what it is. And they get their diffraction pattern. It's all a computer after that. But it's really, there's some heavy-duty math in there, but with software and computers, those guys, it's the synthesis of that beautiful crystal that's the hard part and the frustrating part. Yes?
So all of those lines are equilibrium lines between the crystal formations?
Yeah. So isn't that odd? There's some, you see Adriana's question? It's really hard for me to visualize this, right? There's some equilibrium. I think what that is that's the transition line from one ice to another, right? So there,
get back to its most stable form. Because even if you increase the pressure so much that you're on ice 4 or 5 or whatever the hell, isn't it still going to be trying to get back to the most stable form of ice at whatever angle that is? That one.
well, it depends on the pressure and the temperature. So I like what you're saying. It's trying to get back to the most stable form. It does that according to its chemical potential. It does that according to the phase diagram. What I'm trying to say is you are at some pressure and temperature. Then you move to, I don't know, this pressure and temperature. It's going to do whatever it needs to do to get to that ice 5. Because that is the lowest. That's the chemical potential at that pressure and temperature. That's the molar Gibbs energy. It's got to get there. We don't know how long it's going to take, but it will get there sooner or later. Okay, according to the phase diagram. Okay. Let's see. No, you're not. Have you ever ice skated? No. You've seen it on TV, though. Right? You pull out an ice cube from the freezer. Is it rough? Well, it's not super slick, that's for sure. Right? Everyone agree? It's not super slick. So how the heck do people go wee, woo, and spin? And I'm not mobile enough, but you know what I mean. Okay, you get the nice Zamboni machine out there, right? Get it nice buffered and stuff. Rob, have you been on a surface that's been Zambonied?
Yeah.
Is it?
It's
If you what I'm saying is you put your hand on something on that ice and don't. I'm not talking about stepping on ice. I'm talking about just feeling it. There's a lot. It's friction, man. It's not a smooth surface at all. In fact, it starts sticking to your hand and things, right? So something's got to be going on with pressure and ice to make ice skating work. Can you see what it is? There's a real jump to get there, but you might be able to see it by looking at the phase diagram. You might be able to see it, why people can ice skate.
Is it because the triple point is so low?
Mm-mm. So where are we talking about? Let's circle it first. Let's pick on
I always thought it was
Amberly. I want to circle the area on this phase diagram we're talking about. We're talking about people ice skating, and what region on this phase diagram are we supposed to be looking at? Where exactly? Give you a hint. What's the pressure on the ice skating rink? When you go ice skating, what's the pressure? It better be, right? It better be around 1 atmosphere, right?
So then we'd be looking at around the normal freezing point.
Around the normal freezing point, right? You can't make it any hotter, otherwise you're not going to have any ice in the first place. So we are looking, I don't know, and the temperature, who knows how cold it is, but the point is you're looking somewhere around here, right? Okay. It's hard to see, but it's there. As you crank up the pressure, what's happening? What does that line represent, first off? Yeah, I know. What's the word, though? What's the word that represents that line? Yeah, equilibrium's going on between what and what? Solid and liquid. What do we call those points? Yeah, we call it fusion, but only you call it fusion. Everyone else calls it melting points or freezing points, right? Melting points. There's a hint. Crank up the pressure. What's happening to those melting points? They're what? I don't know. Look at the plot. They go down. If you crank up the pressure, because the line is, it's really hard to see. The line is bent backwards or is it bent forwards? It's bent backwards. The line is bent backwards. So you crank up the pressure, right? The freezing point's going down. So as you crank up the pressure, is it getting easier or more difficult to melt? You crank up that pressure, easier. It melts at a lot, right? A lot lower temperature, right? Okay. So that means it's ice, right? You step on the darn thing. You put pressure on it. The melting point of the ice that's below the heel of your boot where all that pressure is. It's not, because right before you even stepped on it, it's at equilibrium, right? But now you change the melting point. Oh, you really lowered it. The heel of a boot is sharp. You add all your weight, because what's pressure? It's what over what? Pressure is, Kathleen, what's pressure? What over what? Pressure is force per unit. What squared?
Oh, meters squared.
Meter squared. Surface area. Pressure is force per unit area. So under a heel, under your heel of your boot, a lot of area or a little bit of area? Very, very, very tiny, right? Especially you hit this on your heel, right? Very high pressure because the area is so tiny. You drop that melting point like a rock, the ice, the solid, immediately turns into what? Liquid. It's hot under that, well, for the ice.
Yeah,
For the ice, it's super hot. I mean, it's supposed to, you know, melt at a really low temperature. Not for it. It thinks it's really hot. It turns into a liquid like that, right? You slip, fall on your... Now the pressure's off. The melting point goes back to where it should be. It immediately what? Freezes. So what is going on with ice skating? They're not skating on ice. They're skating on what? Water. That's why it's so damn slick. It's super slick. They're skating on water. Okay. Now, what's peculiar, I guess we'll talk about this more, but water is... Do a lot of compounds do that? That their melting point decreases with pressure. Now, I don't know how you'd know this, but this to me is one of those, I don't know, I guess you call it I call it a God thing. There's no other explanation. A God thing. Because the reason why I say that is the implications of this are astronomical. They are huge. It's the reason why we have life on the planet. A line going back. Every other compound known to man, the line's going.
Isn't that how you recognize the water?
Why? And we'll get into that a little bit more, why it's such a big deal. But it's just, you know, I don't know how else to explain it. No one else. You know, it's very peculiar. Anyway, since we're at a Catholic school, I can call it a God thing, right? I don't know how else to explain it.
Doesn't the same thing happen with boiling points?
Okay, now
But not with water, isn't it like pass upwards for water?
boiling points.
If you increase pressure, doesn't the temperature?
Well,
I thought that's why we did back.
boiling points are going to be doing a number of different things, but like look at this boiling point. Wow, oh, this is different. We'll talk about him. Here, most boiling points are like carbon dioxide and water. They're, what's that? Is that concave? Okay, concave. Okay. So I think most everything's like that. This isn't going to be an oddball down here. But when you're talking about life, boiling doesn't really have anything to do with anything. He's dead by then anyway. So, but this is going to have something to do with something. Anyway, we'll get to that. If you take a look at this plot, this is
Isn't it helium?
helium. There's a lambda line in there. I think these plots almost need to be 3-dimensional, 4-dimensional, something like that to really bring this point across. What two states can never be at equilibrium for helium? That's helium. What two states can never be in equilibrium? Which is called what? What process? Starts with an S? Sublimation. Sublimation can never occur. Sublimation can never occur for liquid helium. Solid and gas, gas solid can never be in equilibrium. Lambda line. Okay. Superfluid. I should have brought in my... Mad, you've played with this, I think. That you take cornstarch, we add a bunch of water. What happens? I think you played with this, haven't you? No?
Not on purpose.
Okay, you played with it, right? What was the big deal with it?
When you took a stick and you shoved it in there and you tried to move it around fast, you couldn't, it was like solid.
Yeah.
But then when you did it really slow, like liquid.
Yeah. Do you hear?
Yeah.
Explained very well. So that's your guess. Would that be called what Adriana just explained? Would that be called a Newtonian fluid or a non-Newtonian fluid? Is it behaving like typical liquids or the opposite of typical liquids? It's behaving the opposite, so I call it a non-Newtonian fluid. But what I'm driving at is viscosity is complicated. Viscosity is complicated. What's a superfluid? No viscosity. Something that flows with no viscosity. Okay. So that can be like we had a supercritical fluid. I guess I don't know where superfluids are on here. Oh, there it says it.
It's labeled right there.
Superfluid. Okay. No viscosity. Man, it'd be neat to have a movie of that, right? What would that stuff even look like, flowing in a bucket or whatever? Maybe it's just more floppy is all. I don't know. Maybe it's a pretty boring movie, so nobody made a movie of it. I don't know. Yeah. Okay, here. If you understand viscosity, if you can answer this question. What oil in your car do you want to put, a really viscous oil or a very low viscous oil, if you're in Minnesota and it's January?
No.
What
No,
type
the-
of oil
usually
would you
that
want
was
to put in
the-
there?
was, what the engine worked.
Really highly viscous or very low viscosity?
See, I asked you what viscosity, now you're asking me, that's just rude.
No, but you know what? It's really cold.
Yeah.
What property would you want that oil to have?
Oh, very
I
high
want it to
viscosity.
be more liquid.
You want it to be really what? Don't use the word viscosity here, because you're trying to figure out what that means. You want that oil to be really what? Now it's really cold. If you start out being really thick,
No, you don't.
you make it cold, it's going to get even thicker, right? So you want it super thin, right?
You want it to be fluid.
You want it really to be fluid. So is that low viscosity or high viscosity? It's low viscosity. It's low viscosity. Okay. The resistance to flow is viscosity, probably. Thermodynamic criterion for equilibrium. The chemical potentials everywhere. I tried to illustrate that, maybe not so well with that movie with the boiling and zero gravity. That whole bulk fluid is just trying to turn into a vapor all at once. Okay, so when you're at equilibrium, it doesn't matter what state you are. That's the whole point. That the chemical potential is the same for both states. So you're at equilibrium. Okay. And that idea is what is going to drive some of these derivations, the math down below. Okay. So, stability on conditions. They're just trying to say stuff like, we're going to get out of this. Why does the melting point, if you crank up the pressure, why does the melting point go up? Why does the melting point go down? What happens to the vapor pressure as the pressures increase? Those sorts of questions are what we're starting to answer, okay, with these relationships. It looks, though, if you take a look at this partial derivative right here, it looks like pressure has the biggest effect on chemical potential. Pressure has the biggest effect on these phase diagram plots. With what state? With what state? A gas, why? Yeah, well, they take up the biggest volume too, right? Yeah, molar volume. Their volume is the largest. You take a little bit of liquid, convert it into a gas. The molar volume, you can't even compare the two, right? Liquid volume is insignificant in comparison to a vapor volume. Okay. Partial vapor pressure. I take a drop of liquid, put it in this room, Alice's. I don't know what that is, soda or whatever, right? Mostly water. Put a drop on this table. Okay. And I don't know, somehow it doesn't evaporate. that means we must have a lot of buckets of water in here, right? Because there has to be an equilibrium going on. Otherwise, the whole thing's going to evaporate. So it might take a lot more than a drop. Maybe we have to have buckets all over in here. But the point is that you can put a drop on this table, and it stays in equilibrium. Are you with me so far? Okay. PV equals nRT. So in this room, we have to have everything, it has to be in equilibrium, so everything has to be sealed up. Because if you have a window open, now you're in equilibrium with the outside, so you're never going to get there. Right? So everything has to be sealed up, the doors, everything. V would be the volume of the room. If I write N to be just the number of, what's little n? Moles. If I make it just be the number of moles of water, R is gas constant, pick it, T, temperature of the room, V, volume of the room, what would P be? The pressure here is 1 atmosphere. But the technical jargon, what is P? It's just right next to it. Vapor pressure of water. You could look it up in a table. You know exactly what it is. Right? It's the vapor pressure of water. You could look at a phase diagram and get it. Right? See what the temperature is, go across, see what the vapor pressure is. Right? Wouldn't that work? Find a phase diagram for pure water, see what the temperature is, go across. Oh, that's my vapor pressure. Okay. Right? Does that make sense? Vapor pressure is going to might be really low, but that's fine. Because that means if you sucked out all the air in here or reduced the pressure down to that vapor pressure, that little bubble is going to start. Well, it's always going back and forth. It can start the B word. Boiling, right? Because at the same chemical potential as the liquid state, the gas state, the same chemical potential. Okay. So let's see if we can derive some of these green lines, right? The phase boundaries. That's what all this is about. And what we did, we set this equal to, right? Delta S was delta H over T. Do you remember doing this? We did it in the concept review, and then we derived this. We did that. We derived it. We just derived the Clapeyron equation. We derived the plot. So remember phase diagrams, you're plotting what and what? On the y-axis it's pressure, x-axis it's temperature. So how does the pressure vary with temperature? And you want to be at equilibrium between the solid and liquid. There it is, the Clapeyron equation. Pick a pressure and a temperature, and then you know what the other pressure and temperature are. Clausius-Clapeyron equation. Did we derive that one? I don't remember if we did or not. Yeah, because D, remember this? Remember the trick for that? D ln P was really, remember how it started? 1 over P dP. That's how we started out. The D ln P, we rewrote that as 1 over P dP. And then we did our whole derivation again. So we derived the Clausius-Clapeyron equation. Liquid vapor boundary. Okay. Let's see. So with this liquid solid, right? If we go back up to this. If we have a positive slope, right? You crank up the pressure, positive slopes, I guess that's right. And Crank up the pressure, chemical potential increases, positive slope. We're talking about the liquid and the solid. Which one's bigger? And right. So we're positive slope. We're going that way. So you're heating things up, so you're going from liquid to solid. You have a positive slope. Bless you. Final minus initial is your how you do changes and how you do slopes. You have a positive number, so the molar volume of the solid is bigger.
I get that for water, but will that work for other things too? Is that always the case?
Hold it. Is this right? Melting point. I think it's the other way around. Melting point. Oh, sorry. Sorry. Let's think of melting point. We're going the other way around, isn't it? Melting point, solid going to liquid. So think of melting point. We should get that word fusion out of my head. Solid going to liquid. Yeah, sorry. Solid going to liquid. So one minus the other. Final state minus initial state, positive. Right? So that's usually how it works. Okay. So most everything has a positive slope, like this guy. Except waters looks how? Going this way. There's waters. So for water, the volume of the what is bigger? The solid is bigger. Okay. That's why ice floats. If the volume of solid ice was not bigger than the molar volume of liquid water, how would lakes freeze? How would they freeze? Right now, imagine what happens. Where's it coldest in a lake? It's starting to freeze. It's getting cold. Where's it coldest? I would say at the bottom, right? Because less sunlight and stuff. Okay, so that's where your first little ice crystal is going to form. Where does it go?
Right to the top.
Why?
Because it's less dense.
It's less dense. Is its mass any different? No, its volume is. So it's less dense. Molar volume of the solid's bigger, right? Okay. Think of a typical substance, right? Where is it coldest on the lake of benzene? It's coldest on the bottom. You get a little ice particle to form. Get a little benzene frozen particle to form. It's going to sink to the bottom. So if water was just like every other compound known to man, lakes would freeze from the bottom up. Could those little fishies ever, evolution? Nothing. Nothing could evolve. Nothing. So, well, you wouldn't have any people or worms or anything in the first place, right? Okay. We talked about that. Okay, let's just make sure you're following me here. So on this plot, does melting point increase or decrease with temperature? It increases, right? Okay. That's how most compounds are. Every compound, pretty much. How about here? What's with boiling point? Does it increase or decrease with pressure? Increase, right? Does that make sense? Crank up the pressure, because when do things boil again? When do things boil? What was the trick to getting something to boil? What had to match? Two things had to match. The vapor pressure and the external pressure. Right. Once they're the same, things boil. So if you crank up the external pressure, yeah, I mean, it's going to take a much higher vapor pressure to reach it. So you got to crank up that temperature even more. Okay. I think that's enough, right? Let's see if we can take a look at our questions. So this mess of equations that we have here, what seems to match. I have my equations.
Holy crap. More useful?
What are you going to do to answer one?
I know.
They want to know the temperature at which its vapor pressure is 500 torr. That fits perfectly with whose equation? What's the name of the dude? Or dude people? Clausius-Clapeyron, right? Because that's Clausius-Clapeyron talks about this type of thing, equilibrium between the liquid and the vapor. So, where is it? Clausius-Clapeyron. All right, they just need to give us that information.
Estimate the temperature. Awesome.
Okay. So do they give you, if you look at the Clausius-Clapeyron, you need a T1, a T2, a P1, a P2. And they gave you those, right? Everyone okay with that one?
They gave you yeah, you're looking for one of the T's.
Oh, you're looking for one of the T's. But temperature, just always put it in Kelvin. Yeah. Okay. And we did some problems where we showed that units were consistent. So that is another guide on how you should be worried about units with the concept review. We talked about, we messed with those a little bit. So that's what you pretty much follow what we did in the concept review. In 2, the molar volume of a certain solid is 161 cubic centimeters per mole. So they're not talking about boiling anymore. Talking about melting. Find the enthalpy and the entropy of fusion. If we go back, all right, aren't we talking about melting now? So not Clausius-Clapeyron, but just the one that he did by himself, I guess. Right. Okay, there's our enthalpy of fusion. You recognize it? And we did, again, that concept review, I think, falls into play a lot in this. We even had a quiz question on it. How do you get the molar change in volume? But I think they didn't even give us density. They gave us the molar volume, so we don't even have to flip anything. Right? So do you see how to get the enthalpy? We'll just use that Clapeyron equation. But how do you get the entropy then? Yeah, what relationship are you looking at? Yeah, Adriana sees it. Right. But are we, yeah, she said it right too. Are we after a P or a T? No. So we can just use it as a slope. P2 minus P1 It's approximately P2 or P2 minus P1 over T2 minus T1. And solve for what we're interested in. Right? You're okay with two?
How would we set it up for the entropy?
Oh, for the entropy. You said it.
Yeah.
You're right. You said to use this,
The dp/dt. Yeah.
right? So that's. So then you could say approximately. Right?
Is your brain working?
I don't know.
Something like
I know
that.
why I asked that. I think I was looking at the wrong.
Okay.
It's okay. Just turn on my calculator. The last time I was
Okay.
foundations and I could.
So we're okay with 2 and 1? Ready for 4? The vapor pressure of benzene at 10 and 30 fits the expression. The log of P in units of torr is 7.96 minus 1780 divided by T in units of Kelvin. Find the enthalpy of vaporization in the normal boiling point.
Is it the same thing?
Same thing.
Density of
Because we're looking
Well, we're not same thing. This is what we used last time.
for. No, I mean like.
Now we're using, yeah, the one below. Okay. Do we jump to this expression? No, because they told us how does pressure change with temperature? They told us. Right? They had some equation. They had some equation. There it is. That's how it depends on temperature.
And that's just temperature.
But the problem is what? Do you recognize it? There's the equation. How pressure changes with temperature. This is what we're supposed to use. What's the problem? That you're supposed to take the derivative of what with respect to temperature? According to this relationship. The derivative of the log of P. There it is. Now do you see the point of the concept review? You have to convert natural log of P to log of P. Concept review tells you. Right? So rewrite the relationship so that that equation is natural log of P using our concept review. Convert this to natural log of P relationship. Take the derivative with respect to, according to our equation here, take the derivative with respect to, change colors here. Take the derivative with respect to your T. You have your natural log of P expression. Take the derivative of it with respect to temperature, and that, whatever you get, will equal this. Okay. And that's what they were after, that enthalpy of vaporization. How about the second part of that question, though? Because there's a B. The normal boiling point of benzene. Normal boiling point of benzene. What's so normal about the normal boiling point of benzene? notes. Maybe I do. Normal boiling point was in here somewhere. There it is. 1 atmosphere. Right. The boiling point at 1 atmosphere is the normal boiling point. Okay, so we're going to plug and chug, but in what expression? Is it this one? Or is it the one they gave us? It's the one they gave you, because that's they gave you the expression, right? Just watch your units.
So is that pressure in torque?
According to this relationship.
Just use capital P's.
Okay. We have a couple minutes. How about 5? Oh, we're missing something.
Yeah.
2.891.
It changes from da, 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 da.
Oh,
Definitions like 6. How are these exercises? 658?
is it 0.879 to 0.891?
Yes, sir.
That's what I thought. Yeah, okay, so we got it. We're good. When benzene freezes, density changes. Again, concept review. We did this. We had the densities, and we had to get the molar volumes.
Do you just flip and subtract?
That's pretty much it. Watch your units, though. Did you hear what he said? Flip and subtract, but also you got to change the grams to. They want molar volume change according to that, even that expression, to moles, right? And that Clapeyron equation, because what we're trying to use is our Clapeyron equation. Right?
So you just
This guy.
divide by molar mass.
Right? Yeah, so final minus the initial in molar volume, but it has to be cubic meters per mole. So that density needs to get flipped and changed to cubic meters per mole. That's what the quiz was about and the concept review that you had. And that's how you get the delta V for fusion. I think that's pretty much all. That's really the trick to that question, I think. Oh, there's another trick to this, I think. You have to it's freezing. It's freezing. So we're going from what state to what state? We're going from liquid to solid. So what sign do you put on your delta H there? You said it. Negative, right? You're going down the energy ladder. And why is that a big deal? That's a big deal because look at this equation. Look at that equation. The sign you put on that enthalpy of fusion, because you're adding and subtracting that number from something else. You're going to get totally screwed up if you don't put the right sign on there. Oh, am I going from solid to liquid or liquid to solid? Right? That's key. You're going to get really frustrated trying to get the answer to the back of the book if you don't put the right sign on something. So we're about out of time. We are out of time, so have a good weekend.